Welcome to this lesson on structural strengthening versus architectural preservation. In this video, we'll explore the challenges and techniques involved in maintaining and strengthening modernist concrete buildings, which are increasingly being recognized as architectural heritage. The use of reinforced concrete revolutionized architecture in the 1900s, offering unparalleled flexibility in design. Architects like Le Corbusier, Louis Kahn, and Pierluigi Nervi embraced this material for its strength, durability, and the ability to create bold, modern forms. However, many of these structures are now facing the dual challenges of aging materials and the need to meet contemporary safety standards. Unlike older heritage buildings made of stone or brick, 20th century concrete buildings often face deterioration issues such as corrosion of reinforcement bars, cracking, and spalling of the concrete. Many of these modernist concrete structures were designed with innovative experimental techniques, meaning that their long-term performance wasn't always fully understood. Additionally, modern seismic codes and environmental factors have introduced new challenges. Without intervention, these architectural treasures are at risk of severe damage. Structural strengthening is crucial not only to preserve their physical integrity, but also to ensure they can continue to serve as functional spaces in our contemporary world. While strengthening might be necessary, there's also a strong need to preserve the original aesthetic and design intent of these buildings. Preservation in this context doesn't just mean protecting the building's appearance, but also maintaining its historical and cultural significance. The design ideals of the 20th century were often tied to concepts of minimalism and the honesty of materials, making any intervention particularly sensitive. For example, brutalist buildings, known for their exposed concrete surface, present a unique preservation challenge. How can we strengthen this structure without obscuring or altering the very material that defines their aesthetic? One of the most critical challenges for these buildings is addressing seismic forces, as many of them were originally designed without considering or significantly underestimating the impact of horizontal forces. This oversight often means that when these buildings are considered for reuse, a seismic evaluation becomes necessary. Frequently, this assessment revealed that the building do not meet current seismic standard, especially if calculation methods used for new constructions are applied. Understanding Newton's second law of motion is crucial when dealing with seismic forces. During an earthquake, buildings are subjected to lateral forces F, directly related to the mass m, and the acceleration a of ground motion. When approaching structural retrofitting for an existing building, interventions must be evaluated within the framework of ultimate limit state. This method guarantees the safety of a structure under extreme conditions by ensuring that the design action effects ED do not exceed the design resistance RD of the structure's components. Interventions can thus focus on two primary approaches: reducing the action effects or improving the resistance of the building's elements. One approach to mitigate seismic forces is to improve their distribution within the structure. Adding shear walls or steel bracing stiffens the buildings and helps distribute seismic forces more evenly. These elements provide additional support, reducing the concentration of forces in specific areas, which in turn helps minimize damage. However, this system can alter the building appearance or affect the usability of interior spaces, as the additional structural elements may limit floor plan flexibility or obstruct views. Another strategy involves reducing the energy transmitted to the building by incorporating damping systems. These vibration control devices absorb seismic energy and reduce the acceleration experienced by the structure. There are two main types: passive dampers, such as tuned mass dampers and viscous dampers, which operate without external power, and active dampers, which require sensors and actuators to counteract building movements in real time. This system effectively reduces the seismic forces acting on the building and, in some cases, can avoid the need for extensive modifications. However, they can be costly and are often used only where other strategies are not feasible. An additional method focuses on reducing the mass of the building. Non-structural components, such as heavy cladding, secondary flooring system, or interior partitions, can substantially contribute to the building's weight. By replacing these with lighter materials, the overall mass of the building can be reduced. thereby decreasing the seismic forces it experiences during ground motion. This approach is easier to implement and focuses on elements that are not typically part of the building's heritage features, allowing modifications without impacting the original design. To further reduce seismic forces, attention can also be directed toward controlling the acceleration transmitted to the building. One highly effective but complex and costly method is base isolation, which involves placing flexible bearings or isolators between the foundation and the structure. This allows the ground to move during an earthquake while the building remains relatively stationary, drastically reducing the forces transmitted to the structure. Additionally, the dissipative properties of the soil beneath a building can be considered to reduce accelerations. By evaluating the soil's ability to dissipate seismic energy, the forces acting on the structure can be estimated with greater precision. However, this approach requires specialized studies and advanced calculation methods, making it suitable for specific soil conditions where such factors can be effectively accounted. Finally, we can enhance the building's ability to resist seismic forces by strengthening critical structural elements. Localized interventions such as reinforcing columns, beams, or joints can improve the strength of these components. Techniques such as traditional concrete jacketing, steel plate bonding, or the application of fiber-reinforced polymers and advanced cementitious composites are commonly used for this purpose. These methods increase the resistance RD of key elements, allowing them to bear higher forces during seismic events. However, these popular interventions can sometimes result in irreversible changes to the exterior surfaces of the building, potentially altering its original architectural expression. In conclusion, each of these strategies, force redistribution, energy dissipation, mass reduction, controlling acceleration, and strengthening structural elements, offers unique advantages and challenges. The key to successfully balancing structural strengthening with architectural preservation lies in carefully considering the specific characteristics and historical significance of each building. By doing so, we can ensure that this modernist concrete structure continue to stand as safe, functional, and aesthetically valuable landmarks for future generations.